Hi, in this lesson we're going to focus on logarithmic functions. So there is a relationship between exponential functions and logarithmic functions. So if we have an exponential function y equal b to the x, it can get rewritten as a logarithmic function as log base b of y. So x equal to log base b of y. Notice that the base in the exponential equation becomes the base of the logarithmic function, and the x and y switch places on the other side of the equal sign. So log base b of x and x equal to log base b of y, these are considered to be inverse functions. So if you recall, inverse functions have very specific characteristics, so we'll talk about that more later. So in order to convert from an exponential equation to a logarithmic one, the coefficient of b to the x must be 1. So if it isn't, you'd have to divide by whatever the coefficient is before you and get it over to the other side before you convert to the logarithmic form. So just a little reminder of vocabulary. For your exponential equation, you call your b the base and x is the exponent. And when it's written in logarithmic form, this is read as log base b of y. So to convert y equal to the x to a logarithmic equation, this will be x equal to log base 2 of y. So it's basically just applying this definition that we stated here to the more specific example of 2 to the x. If I want to convert this to logarithmic form, the first thing I need to do is divide by 3. So I have y equals 2 to the x. Then I can rewrite this as x equal to log base 2 of y over 3. Again, using the same definition that's in the box above. To go in the other direction, to convert from logarithmic form to exponential form, same idea. You can't have a coefficient in front of this other than 1. So for example, this is ready to be rewritten as an exponential. So log base 3 of 9 is the same as 3 to the x equals 9. So it's just practicing converting from one form to the other, not actually solving it. So we're not being asked to solve this, just rewrite the logarithmic form into the exponential form. Same idea here, except this time I have a -1 as a coefficient, so you need to get rid of that first. So log base 5 of x now equals -2 when you multiply both sides by -1. So therefore, 5 to the -2 equals x. So this is the exponential form of the logarithmic form above. So we can solve these. So suppose I wanted to solve this for x. So it helps to be able to write it as an exponential expression. So this means the same as 16 to the x equals 1/4. All right, so how would that occur? Well, what value would x need to be in order for this to equal 1/4? All right, so remember the square root of 16 is 4, but I have 1/4. So if so this is the same as 16 to the 1/2. So if I need it to be in the denominator, that means that my exponent should be negative. So 1 over 16 to the negative, 1 over 16, I kind of skipped a step here. 16 to the -1/2 would be the same as 1 over 16 to the 1/2, which would give me the 1/4. So your exponent should be -1/2. And we'll learn other ways to solve equations like this in a future section, but this is one method here on the right. So here we have log base 8 of n plus 1 equals 3, so we need to solve for n. So again, rewriting this as an exponential would be 8 to the third equals n plus 1. 8 to the third is 512. Subtract 1 from both sides, you get that n is 511. Okay, here's another one where we're going to first rewrite it as an exponential expression. So y equals 7 to the negative 2, but 7 to the negative 2 is the same as 1 over 7 squared, which is 1 over 49. So different ways to solve your logarithmic equations, but in each case, we first rewrote it as an exponential expression, which is why the definition above was important. All right, so let's talk about the graphs of logarithmic functions. So the graph of a logarithmic function will have these properties as long as the base is greater than 1. So remember, the base has to be positive, but we're first going to talk about the specific example of the base being greater than 1. So the domain will be all positive real numbers, and the range will be all real numbers. The negative y-axis is an asymptote of the graph, so that's the line x equal to 0. If x is between 0 and 1, then your logarithmic function is negative. If x equals 1, then the logarithmic function equals 0. And if x is greater than 1, your logarithmic function will be positive. So once you see the graph, this will make more sense to you. And if x is greater than 1, then x increases more rapidly. So your x's grow faster than your log base b of x. So if b is greater than 1, your graph will be increasing, but if your base is between 0 and 1, then your graph will be decreasing. So otherwise, the rest of the attributes above will be the same, whether your base is positive, greater than 1, or between 0 and 1. All right, so here I want to graph y equals log base 4 of x. So in order to graph this, we need to rewrite it as an exponential function. So that means x is equal to 4 to the y. So we're going to approach this in a little bit of a different way than we normally do. This time we're going to pick values of x and solve for, pick values of y and solve for x. So we're going to be doing things in an opposite order of what we're used to. So your y could be any number. So I picked some negative, 0, and some positive. And then you just plug it into this function, so to solve for x. So when y is negative 2, your x is 1 over 4 squared, which is 1 over 16. When x is negative 1, remember that's 4 to the negative 1, that's just 1/4. When x is 0, anything to the 0 power is 1. When x is 1, 4 to the first power is 4. And when y, I should be saying y this whole time. When y is 2, 4 squared is 16. So notice that your x's grow much faster than your y's. So when you put this all together, this is what your graph looks like. This is the graph of the points here. So 1/16 negative 2 is the first point. 1/4 negative 1 is the second one. 1/0 is the third one. 4/1, and then 16/2. I didn't really show that here because it wouldn't fit on my graph, but it would be further up this way. Because remember, this is going to keep increasing. So it's increasing from left to right because my base is 4. So if your base is greater than 1, it's going to have a shape that looks like this. So just to remind you of some of the things I mentioned above, the characteristics, here your domain is all positive numbers. So your x's will always be positive. Your range, if you look at the graph and read it from bottom to top, it goes from negative infinity to infinity. So this part is going towards negative infinity, keeps increasing all the way to infinity. So your range is all real numbers. The graph is increasing from 0 to infinity. It has an x-intercept at 1, 0. There is no y-intercept. It's not going to cross the y-axis at all. And we have a vertical asymptote on the y-axis, which is stated as x equal to 0. So some of these attributes might sound familiar because they are similar to the characteristics of the graph of your exponential function. Okay, so here's another one. We want to graph this function, but as I mentioned before, first you need to divide by 3, so that's y over 3, and then rewrite it as an exponential expression. So I have x is equal to 2 to the y over 3. So just like before, I'm going to pick y's and solve for x. Now notice that I picked y's that are multiples of 3 so that it would cancel easily with that denominator, and that way I could do it without using a calculator. So when y is negative 3, I would have x is equal to the negative 3 over 3, which is 2 to the negative 1, which is a half. So that's what we put here. When x is 0, it's just 2 to the 0, which is 1. When x is 3, well, that's 2 to the first power, that's 2. And when x is 6, that'll give you 2 squared, which is 4. So in this case, my graph looks similar in shape to the one above. It's still increasing from left to right. The domain is still all positive real numbers. Range is still from negative infinity to infinity. I still have an x-intercept at, sorry, this is opposite. It should be 1, 0. And it's increasing over all real numbers. And the vertical asymptote is the y-axis, which is the line x equal to 0. So here's your x-intercept here. I just wrote it backwards. So I fixed that. All right, common logarithms. So a common logarithm is a logarithm with a base of 10. So when you're writing a common logarithm, you don't need to write the base, and in your calculator, you will have something called a log key. So you should see that somewhere in your calculator, and that refers to a common logarithm base 10. All other bases for anything where you see log would not be on your calculator, at least most calculators, with the exception of base e, and I'll talk about that in a second. So suppose we wanted to evaluate log of 1,000. Log of 1,000 is the same as log of 10 to the third. So remember, my base here is 10, even though we don't see it. And the answer for a logarithm is the exponent. So 10 to what power would give you 10 to the third, or 1,000? Well, that answer is 3. And you can try that in your calculator. Just take the log of 1,000 and you should get 3 as an answer. But you certainly don't need a calculator to evaluate this. Similar here, 1 over 100 is something that could be rewritten with a base of 10. So this is the same as log of 10 to the negative 2. So 10 to what power gives you 10 to the negative 2? Here the answer is negative 2. Okay, anything other than that, like if I wanted to evaluate the log of 254, well, I can't really write 254 with a base of 10 the way I did with 1,000 and the way I did 1 over 100. So there you would need a calculator in order to compute that. Okay. So here's an example of that. We're going to use a calculator to evaluate the log of 0.0640. So this is, again, a number that I would not be able to write with a base of 10, so I can't do that in my head. And you're told to round to the thousandths place or 3 decimal places. So plugging this into a calculator, you would get negative 1.194. You should make sure that you get the same answer and that you're familiar with how your calculator works. So here I've given you a logarithmic equation. This equation is used to measure the flow of water in a channel. So C is equal to negative A log base 10, which is a common log of B over R. And we need to solve for R. So how are we going to solve for R? So the first thing you have to do is rewrite it as an exponential expression, but I can't do that quite yet until I divide by negative a. Remember, you need your logarithm to not have a coefficient. So when I divide by negative a, I get negative c over a equals log base 10 of b over r. So that means I can now rewrite this common logarithm as an exponential, and that means that 10, which is the base, to the negative c over a equals b over r. Okay, so the negative exponent means that I can rewrite it as its reciprocal. So 1 over 10 to the c over a equals b over r. And then if I cross multiply, the r goes over here, and the 10 to the c over a goes to the right, you get your answer, which is r is equal to b times 10 to the c over a. Okay. If you're given that you're taking the common log of n, we call n the anti-logarithm. And the anti-logarithm, in order to evaluate that, we're going to use a key that looks like this. Some calculators have that in their as one of their options. And why is it 10? Because remember, the base of your common log is 10. So if you have that x is equal to the log of n and you need to solve for n, you're basically going to say n equals 10 to whatever x is. In other calculators, they might call this your inverse log key. So you might see INV log. Sometimes it's in the same position of where your log key is. So suppose we wanted to find the anti-logarithm of log base 10 of n equal to 0.929. So you basically need to figure out what n is. Okay, so that means that you're going to do 10 to this power. And again, you need a calculator for this. And 10 to the 0.929 gives you a value of 8.492. That's a rounded answer. So if you're not told what to round to, basically follow the lead of whatever that's equal to. That was to the thousands place. So that one is as well. But most times you'd be told. Again, here we want to find the anti-logarithm. In other words, find n when the log of n, and again, that's a common log, equals negative 6.9788. Okay, so this time my result is a very small number. So this is 10 to the negative 6.9788. Some of your calculators might display it like this. Where they give you a bunch of decimal places and then e negative 7, that means that your decimal would be moved 7 places to the left. So if we use scientific notation in order to write that differently, that's the same as 1.05 times 10 to the negative 7. So again, follow the directions in your homework to make sure that you give it present it the way they're asked. Scientific notation is just convenient, and so that you round appropriately. Here we want to find, for number 15, find the anti-logarithm where your log of n is 8.82436. Again, that means that you have to plug this into a calculator, and so you get this rather large number. And then written in scientific notation, that would mean that you only have one whole number and then a decimal as well as the following numbers. And then you would just put 10 to how many times you moved your decimal point. So here the decimal point gets moved 1, 2, 3, 4, 5, 6, 7, and 8. So that's the same as 6.67360. Notice here I rounded to the times 10 to the 8th power. So again, you would want to round according to the directions that are given in the problem. So just as a reminder, inverse functions are functions that when they're graphed, they are mirror images of each other with respect to the line y equal to x. the domain of the function of one of the functions in between the two inverse functions will be the range of its inverse, and the range of the first function is the domain of its inverse. So in order to find the inverse function, and I'm just going to remind you of things we learned in the past, if I want to find the inverse of this, remember the first thing you do is switch the x's and y's. And then I need to solve for y. Well, in order to solve for y, I have to use the definition that we talked about at the beginning. To rewrite this as a logarithmic function, it will be y equals log base b of x. So y equal b to the x and y equal to log base b of x are inverses of each other. Every exponential function has an inverse function that's a logarithmic function. And so when you have a common log, remember common log means base 10, then the inverse will be y equal to 10 to the x. If you have a base of e, then we use the ln function. So log base e of x is the same as ln of x. It's just a special notation. This is called a natural log. That's where the n comes from. And the inverse of the natural log is the exponential function e to the x. Natural logs are used really often in mathematics, more so than the common log. So we need to make sure we understand that. So here we're going to graph e to the x and ln of x, as well as the line y equal x. Remember, that serves as like the mirror of the two graphs, and state the domain of both. So if you remember back when we first learned how to graph exponential functions, when your base is greater than 1, like e is 2.7 something, it increases from left to right, and it has a y-intercept at 0, 1. Its domain is all real numbers. Its range is all positive real numbers. Here's the line, y equals x. It's this dotted line that goes right between the two. And then my log, my natural log function, is graphed below. Remember, your logs will have an x-intercept at 1, 0. The domain is the range of the e to the x, so the domain is all positive real numbers, and the range is the domain of e to the x, so it's all real numbers. So you can see that e to the x and ln of x are mirror images of each other across y equal to x. Their domain and their range flip, as well as their intercepts. Remember, this is 0, 1, and this is 1, 0. So the y value here becomes the x value here, and the x value in e to the x becomes the y value here. Right? That's domain and range flipping. That's just one example. So since e to the x and ln of x are inverse functions, remember your composite, when you, if f and g were inverse functions, the composite would be x, and the reverse is also true, g of f of x. So this is more specifically e to the ln of x then equals x, and therefore also ln of e to the x is also equal to x. And that's just going back to what the relationship is between inverse functions. So this is true for any base. So if y equal to b to the x and y equal to log base b of x are inverse functions, then b to the log base b of x equals x, and log base b of b to the x also equals x. Again, that composite relationship of inverse functions just reduces down to x. All right, so we're going to evaluate a few of them using that information. We have 5 to the log base 5 of 8. So that's what I just stated here. My base is 5, and my exponent, I'm sorry, no, it's more like this one. So my base is 5, and for both the exponent and the log, and therefore my answer is just 8, the value of x. And then I have e to the ln of 20. And again, e and natural log are inverses, therefore your answer is just 20. Ln of e to the third is just 3. Log base 6 of 1 over 36. Well, first you have to rewrite the 1 over 36 with a base of 6. So that becomes 6 to the negative 2. And therefore, log base 6 of 6 to the negative 2 is just negative 2. So that's just practicing using what we know about the relationship between inverse functions and composites. All right, so that's it for this lesson. Give the homework a try. Good luck.